All right, welcome back. The first talk of the afternoon session will be by Tao Yu from Shenzhen International Center for Mathematics at the Southern University of Science and Technology, talking about quantum trace maps for SLN skein algebras.
Okay, thanks for the introduction and thank the organizers for inviting me. As the title says, we're looking at quantum trace maps for SLN skein algebras. This will be a continuation of yesterday's talk by Dan. He set up a lot of the materials for this talk, so I will be briefly reviewing some of the definitions, not spending too long on those definitions, and we'll move on to quantum trace maps. And just like Dan's talk, this one is going to be very impressionist. I'm not going to give a lot of precise definitions, which is kind of strange given that this is a talk about a construction. But what I'm hoping to give you is the idea behind the construction, and of course, something that's going to be interesting for a lot of you is maybe we can take the same approach and construct quantum trace maps for other types of Lie groups. And one more disclaimer before I start. Some of you probably noticed I got the date wrong. I edited these slides last night, and the 1 hour time difference between China and Korea really messed me up. So there are probably going to be other errors. And also another disclaimer, there are going to be a lot of definitions that don't match the conventions from cluster algebra and probably other areas. So if you see something that doesn't match, there's probably going to be an automorphism of the skein algebra or the quantum torus that will give you the correct convention, but I don't know all the corrections necessary for that. So just ignore those differences when it comes up. Okay, so my talk is going to be divided into these three parts. At the first part, I'm going to very briefly review what you've seen yesterday about character varieties and coordinates and stuff. And then we're going to talk about the specific case of n equals to 2, which is very, very well understood. In this section, I'm going to talk about previous works. I'm going to say some people's name who originally constructed these maps, but I'm not going to introduce these maps using their original construction, but their updated version, so that we can see how it generalized to the higher rank situation. Okay, so the setup, of course, we start with the character variety. It's defined as the set of group homomorphisms from a fundamental group, which is this factor S to a group G, and we quotient by the conjugation action of this group G. And of course, we're interested in the situation where G is equal to SLN. And we studied these character varieties by studying the functions on them, and we're focusing on these trace functions where, given a curve on the surface, the trace function of that curve is just a trace of the representation evaluated on this curve. And last night we also saw, well, we didn't really, Dan didn't really give a definition, but this is essentially what's going on. We have these coordinates. In the SLN case, those are the Fault-Gunterov coordinates. They take value as non-zero complex numbers, and there's a construction telling you, given these coordinates, what kind of representation you can get that have those coordinates. So you have this parametrization by this algebraic torus, and by taking functions on these spaces, we get a map in the opposite direction, which is the classical trace map. Okay, so now we're going to move on to quantization. Where's lambda? Oh, lambda is the triangulation. So the trace map depends on the triangulation. This V is different from lambda because there's extra stuff. Like last time we saw the picture with a lot of triangles, we'll show that picture again. So yeah, V will be a set depending on the ideal triangulation. The map depends on the triangulation as well. Okay, so now we're gonna set up the quantization. So we have this quantum parameter Q hat. It really should think of it as some root of the usual quantum parameter Q. It's just a technical point, we need to take roots of Q at some point. We consider two different ground rings. This is what we call the universal situation, because in skein algebra, if you can define it on this Laurent polynomial ring, you can basically use tensor product to get to anything else. And of course, the classical case is when you have complex numbers and you set the quantum parameter to 1. And just to be clear on what we mean by quantization, starting with a space, we're looking for an algebra over this universal ring, depending on this parameter Q, so that when you form this tensor product, well, Q acts as 1 in C. So in the tensor product, we're setting Q equal to 1, and we need to recover the classical algebra of functions. Quantization is also associated to a Poisson bracket on the space to take the Poisson bracket of two elements of this algebra of functions. You lift them to this quantum situation, take the commutator, divide by this thing, and then we take the limit as Q goes to 1. This is not a precise definition, but this is what you think of it. And this is the correct definition in physics, so we're going to use that. Of course, we are also talking about quantization of map, and it's the same situation. If you tensor with the identity map on C, you should recover the classical map. So our goal will be finding a quantization of the classical trace map. And now we're going to see what's happening with n equals to 2. And the reason to start with this is the classical picture is very geometric, and the construction of the quantum trace map is also geometric. So we can more or less explicitly describe this construction in this setting. So in the SL2 case, the set of coordinates is actually the same as the set of edges in your ideal triangulation. So instead of V, we actually just put the triangulation here. So the way to go from these coordinates to this character variety is, well, we can look at this classical picture from hyperbolic geometry. The coordinates in this torus are these sort of shear coordinates of the Teichmüller space. When you think of, take a point here, you do this construction where you put two ideal triangles in this upper half plane model of the hyperbolic space, where you put -1, 0, infinity here, and the remaining one is your coordinate. You think about an arc crossing this configuration in this way, and then you look at the Mobius transformation that takes this triangle into this triangle that sends -1 to 0, 0 to this square, a fixed infinity, and when you work out the Mobius transformation, it's given by this matrix. If you have a curve in your surface, you just basically lift to the hyperbolic plane, and every time your curve crosses an edge, you get a matrix like this, and if you multiply all the matrices together, you get the representation rho on your curve, and then you can take trace to get the classical trace function. One thing I want to point out about this matrix is that there's a 0 in the bottom left corner. We will see how this happens, how this relates to the quantum trace map in a moment. Okay, so coordinates. The coordinates are associated to the edges of the triangulation, so we can put these dots on the edge of the triangulation. And for the quantization, we also have the Poisson bracket, and there's a very simple description. I'm using the letter Q here. In cluster algebra, this is probably the epsilon ij. And it's defined as the sign adjacency matrix of this graph. So if this is E, this is F, then QEF would be 1, and the other way would be -1. A feature of this diagram is that it's local. So what we can do is we can cut open the surface along the arcs of the ideal triangulation, and then we obtain these graphs in the triangles. And of course, we can recover by just gluing these together. And if we look at the map here, one variable in the original surface becomes two variables. So we can write an equality like this, and then because these are in disjoint triangles, these new variables would actually Poisson commute with each other. Okay, so moving on to the quantum case, let's recall the Kaufman-Berkes skein algebra. It's a quantization of the SL2 character variety, and we have these two local relations. The normalization is a little bit different. Here I have q to the power 1/2, and this is minus q plus q inverse. I think in those called the q 1/2 will be A. Because we just described the Poisson bracket between the coordinates in the algebra torus, we can directly write down the canonical, well, standard quantization of these. We just take this non-commutative algebra that's basically the Laurent polynomial algebra, but with this Q-commuting relation. This will be the quantum torus. So because our coordinate here is xe squared in the hyperbolic picture, this will be the square root Chekhov-Fogg algebra. We're going to ignore the subtlety of taking roots, but it will come back to haunt us at some point. So the original Chekhov-Fogg algebra is basically the subalgebra of this generated by squares, or alternatively, you can consider it as a different quantum torus, where you just multiply this matrix by 2 squared. Okay, so because the quantum torus is basically just a Q deformation of the Laurent polynomial ring, we have this very nice basis, symmetrized monomial, normalized monomial, whatever you want to call it. And of course, it's indexed by this vector. The convention here is we take vectors to be row vectors, which means multiplying vectors with matrices are going to be a little bit strange because the matrices will be to the right of the vector. It's a choice we made a long time ago that we have to live with, but that's the convention here. And if we define this a normalization of monomials, instead of simply adding this, we have these extra factors when we take the product. And there's this subspace where we only take monomials with non-negative exponents. We're calling this quantum space short for quantum affine space because it's a quantization of the affine one, not the quantum torus anymore. And this will show up somewhere in our construction. Okay, so previously I described this operation classically using the semi-classically, let's say, using the Poisson bracket. But now with the quantization, we can actually do it on the level of algebra. Instead of just saying we have new variables and some new Poisson brackets, I can actually define an embedding of the quantum torus where the whole thing embeds into the tensor product of all of these factors. And it's exactly what you expect. A variable here is sent to the product of these two copies. Okay, now the Chekhov-Fogg algebra has this very nice cutting situation where we can localize these calculations. The non-commutativeness is localized into each triangles. Well, what we want to do here is develop a similar story for the skein algebra. And when you think about curves on the surface and cutting them along edges of the triangulation, that means we're dealing with surfaces with these boundary arcs, and our curves are going to become arcs that ends on these boundaries. So we need to enlarge our class of surface a little bit. We start with a compact oriented surface, S bar, and we remove a finite set of points. These are going to be the punctures. The punctures are allowed to be in the interior surface or the boundary of the surface. But when our surface is non-empty boundary, we require that every component of this closed surface has at least one puncture. So the boundary of this new surface will not have any closed boundary components. Every boundary component of the surface is going to be an arc. And these components are what we call the boundary edges. And then we need to enlarge our class of curves in the surface into tangles in the surface, which would be smoothly embedded one-dimensional submanifold. Of course, it comes with a framing as well, just like the skein algebra, but we do have some conditions on the boundary. So, of course, the boundary of the tangle has to be on the boundary of the surface, but in the thickened direction as well. The framing at every endpoint of this tangle needs to be vertical and upward, just like the blackboard framing, but we need to impose that on the endpoints as well. And finally, when you look at this tangle ending on the same boundary component, they have a vertical ordering according to height, and it needs to be, the height needs to be distinct. Now, I do want to draw a little bit picture because this will be relevant for a later talk, probably. So imagine that I have a surface like this, where this is part of the boundary. I look at the thickened picture. Where my surface is embedded in the middle. When you look at these conditions on the boundary of the tangle, what you're supposed to think is there's a perpendicular direction pointing upwards. You can think of my alpha 2 and on this vertical arc, then the last condition just says the endpoints on this arc needs to be distinct. There's a height ordering on here. Okay. And of course, we need to talk about diagrams for these tangles. And here's our convention. Our arc ends on the boundary, so our diagrams are going to have these endpoints on the boundary as well, but we do need some way to encode the height information, and we do so by drawing these arrows on the boundary of the surface, and the convention is the closer you're to the tip of the arrow, the endpoint is higher. So for example, this is actually an isotopy of tangles, where if you take this higher endpoint and move it across the lower endpoint, in addition to switching the order of these and reversing the direction of the arrow, you also create a crossing, and this strand is over that strand because this is higher. An alternative way to think about that is you draw the diagram by tilting this vertical arc a little bit so that it's transverse to the projection. Then you can see that if you do it this way versus that way, one of them will create a crossing like that. And this is also important for stacking, because sometimes stacking diagrams will create more crossing than you expect. For example, if you stack this diagram above this diagram, naively you would think the new diagram is this, but depending on your orientation of the boundary, you could either end up with this crossing or not. Okay, so now that we have the class of tangles, we can think about the skein algebra. In addition to these endpoints and heights, there's also states, which is just a map from the set of endpoints to a two-element set 1 and 2. So you can see that these diagrams are decorated with these labels. These two relations are the relations from before, but these are going to be new relations. And interpretation is just like all the others. If you have a local diagram where you see something like this, well, this one just sets to 0. But if you have a diagram where locally it looks like this, it's a scalar q to the quarter times a new diagram with this component removed. Similarly for the last one. Yes? Okay. Oh, the -1 to 1 is any interval works here. this is just the thickened surface, right? The fact it's -1 and 1 doesn't matter. It's just the interval. The 1, 2, we'll explain what 1 and 2 are, but I can spoil this. You should think of these labels as the weight vectors of the standard representation of SL2. So the 1 and 2 doesn't have anything to do with the -1 and 1 from before. Okay, so these are the relations. And here's the whole point of doing this whole construction. We want to be able to cut the surface open and obtain an algebra map like this. So we start with a surface and let C be an ideal arc. Let S prime be the result of cutting the surface along this arc that you choose. Then we have this algebra map from the original static skein algebra to this cut open skein algebra defined by this example. Well, it's pretty much what you expect. Well, you cut this open, of course, you get diagrams like these, but the new endpoints created by this cut process doesn't have states. What do we do? Well, we just sum over all possible choices of states. And the relations here, this set of relations, are exactly what you need for this to be a well-defined map. To see this, you can just think of some elementary isotopy that's relevant to this arc. For example, if you have an arc that goes like this, it should be isotopic to this. So on this side, the two tangles will be equal. But after you split them open, they're no longer equal diagrams. On one, you will have this returning arc and go backwards. But for the other choice, you'll simply have this, but no arcs on this side. So just by checking what makes this map well-defined, you will actually see that these are the relations necessary. So the relations don't actually come from nowhere. Next, technically, we already have all the necessary ingredients to define a quantum trace map, but we want to take it a little bit further and see what's the structure behind it. So we have these structural results. And the simplest surface we can describe using this formalism is going to be polygons. So let pk denote the disk with k punctures on the boundary. Then we have these results. If you only have one puncture, then it's just this, just generated by the empty tangle, so it's R. The key point here is it's not the zero module. And for P2, this is the interesting one. It's actually isomorphic to OQSL2. I didn't write down the definition of it, but it's just quantum matrix functions. And the ij element of SL2 is represented by this tangle. And finally, we have this result where if you glue two surfaces along a triangle like this, so imagine this is S1, this is S2, and this is a triangle that we're gluing them, and they're glued on along these two edges. Then the static skein algebra decompose as a tensor product as a modules, but not as algebras. If you want to get the algebra structure correct, you need to take the tensor product in some braided tensor category, but I don't want to define that. A special case is really interesting because triangles are what we're interested in for quantum trace map. And this tells us the static skein algebra of triangle is tensor product of two copies of OQSL2. You just connect this side, and see a triangle is just two bigons glued along a triangle. Okay. We can even say more about this bigon situation, the OQSL2. Previously, the static skein algebra, it's just an algebra, but actually you can recover all the structures of OQSL2 as a Hopf algebra. There's even a co-R matrix on on OQSL2, we can recover that as well. But in particular, I want to point out just these two parts, the co-multiplication and the co-unit, which is very easy to understand geometrically. The co-multiplication is just the cutting map in the middle. So you have I and here, J here, K in the middle is the sum over states of the cutting. And the co-unit is just the identity matrix. Moreover, for any surface with a boundary edge, you can cut along an arc that's parallel to the boundary edge, and then you will have a surface that's equivalent to the original one, but now you have an extra component that's a bigone. So we obtain a cutting map like this, but this is OQSL2. So, and the conclusion here is that it's an OQSL2 coaction. In particular, if you apply coaction and a co-unit on this factor, you obtain the identity map. Okay, so remember a long time ago, I told you that the matrix has a 0. Now we're going to do this. When you have an arc going like this, and when we pick out this specific matrix element, we can actually consistently set that to 0 in a stated skein algebra, and we obtain a new algebra called the reduced skein algebra. And a very appealing fact about this arc is that if there is a cutting map right through this vertex, you can see that whether no matter you put 1 or 2 here, at least one of these sides will be the same form as this one. So the cutting actually descends to the quotient that is the reduced skein algebra. And now I'm going to finally define the first quantum trace map, which is given by Bonahon-Wong, but probably not in this form. So what we do here is if we start with the surface, we go to the reduced skein algebra, cut along all the edges, and then now the surface is just a disjoint union, a bunch of triangles, and then we get a tensor product of 1 for each triangle. And then we use this specific formula to go from this reduced skein algebra of a triangle to this quantum torus of a single triangle. This is the map that we talked about before. This quantum torus cuts into these little pieces, and it's not too difficult to show that the composition of this lands in the image of this, so you lift back up to a map like this, and this is the quantum trace map. Oh, a bad arc is the arc from the last slide. So the 1 and the 2. Yeah, and note that the 2i minus 3 and 2j minus 3 is just saying if the state is 2, then it's a +1. If the state is 1, it's a -1. Okay. So that's the definition of a first quantum trace map. I'm going to talk about a different version. A lot of people probably wouldn't think of Muller's result this way, but it does define a quantum trace map. So the observations here are the follows. We can actually identify a copy of this quantum space inside the reduced skein algebra, and actually, for an edge E here, I can just take this arc, and it will turn out that they generate a subalgebra inside the reduced skein algebra that's isomorph. That has the correct Q commutation relation. The issue is these arcs don't actually have inverses in the state skein algebra. But what we can do is simply localize this embedding, and then we will get the entire quantum torus. And technically, the localization will give you a map from the quantum torus to a localization of the reduced skein algebra. And there is a second fact here. The image of this embedding is big enough so that the localized map is actually an isomorphism. The inverse of that map will be our second version of quantum trace map. And of course, if you have two different definitions, you need to show that they're you want the fact that they're the same. So of course we have this result. The Miller's map maps into a quantum torus. The Bonahon-Wong quantum trace map is another quantum torus. They're actually different quantum torus, but there is actually embedding going from one to the other, and the two maps commute with this embedding. All right. So that concludes our discussion for n equals to 2. We're going to take the exact same ingredients and try to do this for all SLN. Okay, so to start, we're going to look at the quantization of the SLN character variety. There are actually a few different versions. I'll say more once I show you the defining relations. This particular version is defined by Les Sigora in 21. What we're going to use are these webs that Dan mentioned last time. These are smooth, quote, embedded graphs with orientation and framing. The graphs can have vertices of valence 1 or n. If your manifold doesn't have boundary, then you're actually not allowed valence 1. If you have valence 1, they all have to end on the boundary as the endpoints of this graph. And we have the same restrictions, just like this picture. They have different heights, and there are certain framing restrictions on what can happen, but that's the basic idea of what's going on with the web. And then the SLN skein algebra is defined by the span of these webs quotient by these relations. It looks like a lot, but this is the simplest version that we have. These relations aren't random. Of course, you've seen this. This is the Humphrey relation. There's a framing relation. There's a unknot relation. There is this very, very long relation, and there's a similarly long, very big sum that involves this vertex. You have these kind of returning arc relations that's similar to the state skein algebra. You have this relation where a cup like this is written as a combination of sum like this, which is similar to before. And then there's this braiding relation. The reason that these aren't coming from nowhere is because they come from risk-taking derived construction. What you do is you want SLN, you look at representation theory of UQSLN, and these diagrams represent certain morphism between the certain modules. And for example, this relation is just saying if I have n copies of the standard representation tensor together, I do a quantum antisymmetrization and project to the trivial representation and then include it back into the n copies. I get this determinant-like formula. You can do the same interpretation for all the other ones. For example, this will be the evaluation. This is going to be the co-evaluation once you interpret everything correctly. Yes?
Can you say with the white and the black dots?
Oh, yes. Good point. Thank you. All of these relations are sort of invariant under reversing orientation. So these dots are just certain orientation that's consistent in the picture. So I can fill in all the white dots with an arrow to the right or an arrow to the left. And if you see two different colors, then there are opposite orientations.
Do you have the equation?
I mean, what I said was that this diagram corresponds to the evaluation morphism. This is the co-evaluation.
With the breakdown.
Yeah, because co-evaluation will have V and V dual. So they have opposite orientation. Yeah. Right. I'll explain a little bit more. So what happens is a single strand is going to be either the standard representation or its dual. And when you have a picture like this, you pick one of the direction as the standard representation, then the opposite one will be the dual. So when you look at this, there's V tensor V dual. So when you read it in a certain direction, it's co-evaluation. Yes. So, before we say more about the Versteegen-Torell theory, I do want to mention that if we specialize this big list of relations to n equals 2, we do recover what we have before. One of the key points here is certain combination of relations actually tell you that the element is independent of orientation when n is equal to 2. And then I took some of the relations from the last slide, specialized to n equals to 2, and then if you delete the orientation information from all of these, you'll be able to check that we do get all the relations from Kaufman bracket, and Kaufman bracket will also imply these relations as well. For example, the last one, you have this. Forgetting the orientation is just a crossing resolved that way. You have a crossing, and you have the crossing resolved the other way. Okay. Finally, this is what I said before, but just in writing. We are looking at SLN skein algebra. We consider the quantum group UQSLN. We look at its representation theory. Now, this version of skein algebra is obtained by considering a subcategory where the objects are the standard representation, the dual, and its tensor products. So how do you find all the relations of the skein algebra? You look at this subcategory, you look at what morphisms there are, and then that's how you decide you need to add a vertex because you need the anti-symmetrization map. And then you find all these relations, you draw them as diagrams, you obtain this list of relations. There is another approach, which is probably more natural when you think about representation theory. So instead of just the standard representation and its dual, you consider all the fundamental representations. So now what happens is, instead of just orientation data, you need labels to tell you which fundamental representation you have. And then the anti-symmetrization also becomes a lot of different versions, and they look like trivalent vertices. So we're going to have a lot of trivalent vertices appearing in our skein algebra. There's going to be a lot more morphisms and a lot more relations, because you can imagine that you're going to get a relation every time you have different i's and j's. Call this Kamnitzer and Morrison's paper, they have like 3 pages of relations, and they don't claim that they have the full list. So you can actually define a second version of skein algebra using these people's results, but we're going to have a lot more elements and a lot more relations. But a recent work basically shows that if these quantum integers are invertible, the 2 versions of the skein algebra are basically the same. This is not really an issue for us right now, but for example, if you consider roots of unity, then it's a big issue. Then the 2 will contain different sets of elements. Okay. So because we already saw all these ingredients before, I'm just going to go pretty fast. The defining relations are exactly enough so that we can have all of these nice features. If you have an ideal arc in the surface, you can cut it. It's the exact same picture from before, except all the strands have orientations. I'm defining by an example, so it doesn't have to orient this way, but you cut, you get new endpoints, you assign states, you add them up, I forgot to define this thing, but this is just the states are allowed to be 1 through n because those are the weights in the those label the weights in the standard representation. Okay, again, our relation is consistent so that when you consider the monogon, you don't get the zero module. When you consider the bigon, you get the entire OQSLN. Same thing here. We have the Aij function represented by this diagram from I to j. Now, because of the orientation, there's actually 2 different isomorphisms. You can go this way or that way. We just fix one of the isomorphisms. Same thing here. If you glue 2 surfaces along a triangle, you get this tensor product as modules, but not as algebras. But if you want algebras, you can look at some braided version of the tensor product. Okay. Same story here. This isomorphism is not just as algebras. It comes with all the extra data where the co-multiplication is cutting in the middle. The co-unit is given by the identity matrix. If you cut along an edge that's isotopic to a boundary edge, you get this map. Replacing this with OQSLN, you get a coaction. And if you do this coaction, co-unit, then you get identity. The reason I want to include this last fact is to tell you a little bit about what you should look for if you are going to try for other types of Lie groups, because this is really something that tells you that you're on the right track to the group that you're looking for. And what you want to do is find enough relations that you get this isomorphism, you get the identification of the Hopf algebra structure. And what you can do is, once you figure out the bigon situation, you can actually define your skein algebra so that this holds. So for example, if I scroll back to the defining relations, how do I know to get these? Well, I can actually develop the theory of the bigon. So both sides of the surface are now boundaries. And then I look at the representation theory. I look at what's necessary for this to work. And then I basically erase this part of the edge because of the coaction, co-unit construction that tells you that these relations not only holds on the bigon, but actually works for all of the surfaces. Okay. Back. Again, we never really gave an explicit definition of what's happening with these matrices at SLM, but just take my word for it. There are zeros in the classical matrices, so we're just going to set these arcs to 0 from the beginning of the construction. And instead of just 1 and 2, I'm setting the whole triangular part to 0, and we call these arcs bad arcs. Same as before, if you split any of these arcs down the middle, then at least one of the sides will become 0. So you can cut the reduced skein algebra just like before. Okay, now we're finally moving onto the other side of the quantum trace map, where we're going to start with the Fault-Gonchar of algebra. You look at a triangle, you subdivide the triangle into this shape, and the new vertices of the structure are associated to the Fault-Gonchar of coordinates. And we also had this graph before. You just draw arrows on this graph in this pattern. The point here is everything in the interior has double the weight of the arrows on the boundary. For a surface, what you do is draw the same graph on each triangle. You'll notice that on the edge where these triangles glue, you have 2 hollow arrows, but opposite directions. You cancel them. And when we look at the adjacency matrix of this graph, this is going to be the Fault-Gunter of torus. As before, there's technicality with the nth root. We're just going to ignore them for now. Just like before, if you cut open this, we actually obtain this tensor product embedding. So now we're going to aim for the other version that generalizes Müller's construction. So what we're going to do is describe a second quantum torus that maps into the Fault-Gunter of algebra. So now I'm just going to describe explicitly what that map is. For every vertex, you look at the patterns from the previous graph, and then if your vertex point towards that, then this is -1. If there's an arrow from this to the point, you get +1. It do something a little bit different on the boundary of the surface. After this, you get a whole matrix I call H. A little lemma, H is invertible. The inverse, well, it's a rational matrix, but the point is the denominator is exactly n, so when I multiply by n, I get an integral matrix. I define a new matrix P, which is going to be the analog of Müller's construction. I get a new quantum torus, and I get this embedding of quantum tori using this matrix. This combination shows that this map defined this way is an algebra homomorphism, and the fact that H is invertible, so K is invertible, that shows this is an embedding. So now I can finally formulate the goal. We have the reduced skein algebra here as our source. We have two different candidates for the target. This is the Fault-Gunter of algebra. This is the new thing that we defined, and together with this embedding upwards. We want a quantum trace map this way. We want another one this way, and they should commute in this fashion. And of course, now that I already defined the vertical map, you don't actually have to construct both of them, but there are advantages of having two, which we'll see in a moment. The construction here takes a very weird, twisted route. As we'll see, we will actually construct this version for the triangle first, and well, then through this map, we get a definition of the x version for the triangle. This vertical one is the same as the Bonahon-Wong construction, as we'll see in a minute, and then we'll use the isomorphism backwards. Oh, Q is this matrix. P is just defined as this product. There is more direct description of the P, but I don't want to do it now. Okay, so let me give you the statements, and we'll see how much of the construction we can go through. So we want an algebra homomorphism from the reduced skein algebra into this Fault-Gunter of algebra, and of course, we have the second map into the generalization of Müller. What we want is the classical limit of the x version recovers the classical trace map in Fault-Gunter of coordinates. We have this commutative property from before, and this last one is the algebraic statement of Müller's construction. We want to identify a subalgebra that's isomorphic to the quantum space, and in essence, you should think that the A version is just going to be a localization construction as before. There are technical difficulties with what we have right now, but we won't go into that. Finally, a few people are always asking about injectivity. Right now, I think the result is if the surface is a polygon, then these two maps are going to be injective. And finally, we need to talk about what happens with different triangulations. And here's the statement. We have a family of isomorphism of division algebras, the FR is the fraction division algebra of fractions. This is my notation. So for every pair of triangulations, I have this isomorphism, and they behave exactly the way you think would if you don't change the triangulations identity. They compose the correct way if you have 3 triangulations, and of course, they intertwine with the quantum trace map. And of course, because we have 2 versions, you can make the exact same adjustment to get the other one. Okay, so these are the statements. Let's see the construction. Well, we have 2 approaches. We can construct either one first. So let's talk about this one. At the beginning of our work, joint work with Tanglei, my advisor at the time, we learned about Chekhov-Shapiro's paper that has these formulas. The original version contains some errors, so we made some modifications. So the final result is actually different from their new version now, but the basic idea is the same. So even if you look at the classical trace map, there is a formula like this where the trace inside a triangle going like this is a sum of monomials. In classical fashion, when you want to quantize something that's a sum of monomials, you just simply replace them with the symmetrized monomial in a quantum torus. And the result is that this actually works. I'm going to define this sum by an example. By rotation, I can put my arc in this fashion, and let's say my arc starts with state 4 here and ends with state 2 here. In particular, this one is actually not 0. What we do is, in this Fock-Goncharoff picture, I overlay a second graph with the vertex set, the small triangles, and they have certain directions. Because my arc goes this way, all the transverse edges go to the right, and all the vertical ones go up. And we label the size of the triangle with 1 through n. In this example, n is equal to 5. Because my arc goes from 4 to 2, I look at paths from 4 on this side to 2 on this side. In this graph that's matching the direction, there are multiple paths. So that's why there's a big sum here. For each path like this, I associate a vector of exponents. There is a formula that tells you what these exponents are, but I don't think I'm going to define this right now. So that's a formula for the quantum trace map of a triangle. Theoretically, we can just take this and run with it. The only issue is this defines a map using the generators of the skein algebra of a triangle. And to show that this is a well-defined algebra homomorphism, there are a lot of relations to check. And you have these quadratic relations on these arcs, so you have these big sum of paths. It's doable. We actually did it, but we didn't want to write it down, so we found another approach, which is define the other version for the triangle first. That generalizes Miller's construction. In that construction, there are 2 points. Identify the subalgebra, that's the quantum space, and showing that the subalgebra is big enough so that the localization will give you the quantum trace map. So what I'm going to do is show you the elements that generate the quantum space. Every vertex of the Fock-Goncharoff picture can be parameterized by these barycentric coordinates where the total is n. An element with ijk will have these 3 coordinates associated to the 3 edges. And when you have that, I can define an element like this. I have a m-valent vertex in the middle. And if this side is k, I started with n minus 1, and go all the way down to k bar, which is defined as n minus k plus 1. So there's k points on this side, j points on this side, I points on this side. And of course, because I plus j plus k is equal to n, this is m-valent, and we have these n webs. And the claim is we can take these elements and go through Muller's construction, and it will give us a quantum trace map for the triangle. The set of elements of that form, which I denote by G, they have Q-commutating relations described by the matrix P. And well, we didn't directly prove that it's embedding, but it maps into the reduced skein algebra. We can do the localization to get a quantum torus on this side. And on this side, there's a localization of the reduced skein algebra. Now we show that this localization is an isomorphism. So we define the inverse to be the quantum trace map. And then what we're going to do is, well, we have this quantum, this should be a P3. This is a triangle. Combined with the map before, we get the X version, and then we put it through the Bonahon-Wong picture. We cut open surface. You use the Fock-Goncharov coordinates, and Fock-Goncharov has this nice embedding into the tensor product. We show that the image is actually in the image of this embedding, and then we define the map this way, and then we compose with the embedding from P to Q to get the other version of the quantum trace map. Now, if you go through this whole roundabout process to get the A version from a quantum trace map, we actually identify the generators of this quantum torus in the skein algebra. So theoretically, taking this set of elements, you can attempt to go through Muller's construction and see whether or not you get a quantum trace map. We can show that these elements have the correct Q-commuting relations. It's just showing that they generate a big enough subalgebra. That's the difficult part. So we didn't stick with this for very long and took the roundabout way of doing this. One more remark about these elements. It's not too surprising that something like this shows up, because when you think about it, this vertex is the antisymmetrizer. So what happens is you have these total of n points distributed on 3 different sides of the surface. Remember, these are labeling the weights of the standard representation. So what happens is these are simply the highest weight vectors of the fundamental representation, and they wedge together to the whole thing. So this picture has sort of a representation theory kind of interpretation. Okay, I do want to show you one example of why we want 2 different versions, and it's to define the triangulation chains that I showed you. Of course, we do know what happens to different triangulations in the Fock-Goncharov algebra. Remember, I said this is going to come back to haunt us. The Fock-Goncharov algebra in our notation would be the quantum torus on n squared of Q, but our target is bigger than that. Our target is just defined by Q. It contains all the nth root variables. So the Fock-Goncharov, the mutation, the cluster mutation formulas, it only works on this part of the quantum trace, but we need a formula that's bigger than that. So what happens here is the other version, the A version that's related to Muller's construction, because it's a localization, we can do this very neat algebra trick to directly obtain a transition map without basically any work. Starting with this fact, if you look at the A version, the one related to Muller, there is a subalgebra. Upon localization becomes the target of the quantum trace map. So what happens is, if you take the entire fractional algebra, this containment shows you that the fractional algebra is just isomorphic everywhere. So you automatically get this map. And because this is an isomorphism, to get some transition map that commutes with a quantum trace map, you simply invert this and apply this on this end. So without any work, we get the coordinate change map for the quantum trace map. And of course, the two versions of quantum trace map are also isomorphic to each other. So once we get this version of coordinate change, we just define it on the fault counter of algebra by transfer. Okay, I think I'll stop here.